So today I want to talk about learning and control for batteries. And what I hope to do at the end of this talk is give you a sense for how these models and their various forms can play a role in control of batteries to get better performance, and the role that learning plays. The work that I'm going to discuss today is primarily executed by Aaron Kandel, Luis Cuoto, Sehong Park, Dong Zhang, and Hector Perez. So uh, where I want to actually begin is with something motivating. So go back to the late 1960s, at a time when the greatest threat to humankind on Earth was nuclear war, not pandemic. And in this time, there was tremendous innovation, including the race to the moon. And the reason I want to talk about this is because here, what we attempted to do is take a machine and hurtle it from Earth towards the moon. And this machine is moving in space where we have some sensing, but it's very limited. We want to understand precisely, well, the orientation of this spacecraft. And we want to very accurately control its trajectory so we can bring man to the moon and back. Now, keep in mind, this is all done with what would today be called edge computing, right? There wasn't a large amount of computational power on these crafts. So they had models, but there was limited computation power. There was limited control, delay of communication back to Earth, imprecise sensors. Now, meanwhile, around the late 1960s, you had this professor named Rudy Kalman who came up with something called a Kalman filter, wrote some papers on it that was essentially applied math, mostly unintelligible to most engineers and scientists. But they understood that there was some value in this if they could translate it to practical applications. And it turns out that they rapidly did that. And this was a key technology that allowed us as humankind to get to the moon and back. Now, that was in the late 60s, early 70s, where we took on this challenge. And the reason I'm bringing this up is because it's a very similar situation with batteries, in fact. And 40 years later, I really want to give credit to Greg Plett, who I think attended this meeting last year, who wrote what I consider this seminal paper, where he was really, I think, the first to popularize this idea of combining control and estimation theory with mathematical models of batteries. So he wrote this very impactful trio of papers in 2004 using extended Kalman filters and their various iterations here. And what you can see actually is, if you search publications in battery systems and control, right after 2004, when he published this article, the field really took off here. Okay. And in fact, these estimation techniques can be used for things that go beyond just batteries or sending man to the moon and back. In my free time, this is what I'm playing with, is mathematical modeling of pandemics. And if you have a very limited number of tests because you have poor leadership, can you actually estimate the number of infections inside your community, at least in the early stages when it's exponential? So it's a very nice set of tools for a variety of applications. Now, I don't want to talk about COVID-19. I want to talk about batteries today. So the battery controls problem is essentially we want them to be cheaper, higher energy and power density, charge faster, have a longer lifespan, and safer. And in particular, this is often the role of a battery management system. So some figures of merit in a battery management system are going to be the state of charge, the state of health. We also want to estimate and extend the usable energy capacity, extend the cycle life. And today, I'm really going to talk about and highlight our work on fast charge times. How do we improve this particular metric? Now, I really must give credit to this excellent figure to describe what we are protecting against, put together by Dave's group. Now, what is limiting us in terms of charging faster is the fact that there is a diversity, a cornucopia really, of degradation mechanisms that are preventing us from moving lithium ions from one electrode to another very quickly. Everything from SEI formation to lithium plating to dissolution of materials and so forth. Now, I particularly like this figure from Alon Gore, who was previously program director at ARPA-E in this AMPed program and is currently director of Cyclotron Road, now called Activate. While he was running this AMPed program, he described it as follows. We're trying to protect against a number of degradation mechanisms shown on the left, but the reality is that we can monitor extremely little. In the best case, in say an electric vehicle, we might be able to measure voltage across the cell terminals, current going through the cell, and perhaps temperature at the surface of the cell. So this would be analogous to essentially saying, we want to have an F1 race, but we're going to blind the drivers, and they can only feel and hear, and their job is to finish the race as quickly as possible. So this is the important of estimation for control is, can we remove the blinders? Now, if we can remove the blinders, then we can change the paradigm in how we control batteries. So classically, the way that we control batteries is we put upper and lower limits on things we can measure. So these are things like terminal voltage, cell current, even temperature, and this defines the operational envelope. Now, what's interesting, though, is that if we could monitor well the internal electrochemical states that are more directly related to these degradation mechanisms, we can define upper and lower limits on those variables and potentially expand the performance envelope. In fact, I'll even show you that if the performance envelope is defined on voltage and current, it's even possible that you are violating a safety envelope as defined by that green region, these electrochemical states. So that is really our objective here, and in what sense we want to lift the blinders in how we control batteries. Okay, now to do this, we need mathematical models of batteries, which is, of course, is the theme of this meeting. And traditional approaches, at least for battery management systems, are to use equivalent circuit models. These surrogate models that phenomenologically describe how batteries work. However, if we really want to protect against these degradation mechanisms, it's going to be important to actually model out the various multi-physics that describe these degradation mechanisms. Now, quite frankly, in industry, what you'll find is conservatively, I'd say 95% or more of battery management systems are based off these equivalent circuit models. And actually, I think a big factor in that is that the engineers who are trained to design this are typically electrical engineers. And when you're an electrical engineer, everything looks like a circuit. And so that's comfortable and easy to understand. But it's actually really, really important that the communities start talking to each other and we can better translate some of these multi-physics models as have been described throughout the symposium and understand how we can use this for control. And so I like to say that chemistry and controls are like peanut butter and jelly. They truly go together. They are not in conflict. And putting them together is really going to make the tastiest battery that we could hope for. So in my own research lab, we are focused on a number of topics, including model identification for experimental data. Some of you may have seen that work. I presented at Oxford on that before. We also have several generations of these state of charge, state of health estimation algorithms, which progressively add more physics. Importantly, we're trying to make sure that we can get provable convergence there. We've also done some work on fault diagnostics, but what I really want to focus on today is this fast, safe charging problem, and also this one tool called reference governors. So, pushing forward, here's what's going to happen, and trigger warning if you are concerned about machine learning and reinforcement learning making its way into these physical sciences. So what am I suggesting here? Am I suggesting that we're going to collect a bunch of battery data in phase 1, phase 2, something happens, and then phase 3, profit, where maybe this phase 2 is controls in AI? as you'll see, yes, and also no. So we need to think very carefully about how we use these methods. Okay, so first what I want to describe is learning-based control, some extensions and novelties we've made in reinforcement learning to apply to batteries, and then we'll talk about reference governors. All right, so no talk on reinforcement learning is complete without showing some reference to this Nature article in 2018, where folks at Google DeepMind, including David Silver, who has been at University College London, extended Q-learning with various innovations, including deep neural networks and something called a replay buffer, to come up with an algorithm that can beat the world champion Lee Sedol in the game of Go, and they call this AlphaGo. So since then, there's really been an explosion of interest in reinforcement learning. And I'm trying to highlight that with this picture here. What you can see is that shortly after this paper came out, there's really an explosion of articles. But in fact, this has been a topic that has existed for a while. And the first studies of reinforcement learning have actually started in the 1890s by Ivan Pavlov. And about a year ago, I got a puppy, so I started to think about this a lot, how reinforcement learning is used for training dogs. But the idea was that from a pattern of events, you have this agent, as they like to call it, like a dog, which can identify when the environment could render a reward for that particular agent. So for example, if you provide a dog food, then it might salivate, and then you give it the bone. If you ring a bell, then it won't salivate, there's no response. But if you ring a bell and then give it a bone, it'll start to salivate and associate these things. And so now after conditioning it, when you ring a bell, it will salivate even if you don't give it a bone. And my puppy is sleeping right now, but I was hoping I could actually call her name and bring her over right now to give you an example, but I'll say that for next time. Okay, and the history between the 1890s and 2018 is in fact quite rich. In fact, Richard Bellman in the 1950s derived dynamic programming, an area of optimal control, which really has been the foundation for these methods. And then in the 70s, all the way to the 90s, you have Paul Werbos, who actually most recently was a director at the US National Science Foundation, who really created this backpropagation algorithm and truly created the first notions of using what is now deep neural networks, but he called it heuristic dynamic programming. Then at the other UK university that we shall not name, there was a PhD graduate named Chris Watkins, and as his PhD thesis, he formulated what is now known as Q-learning. And then Dmitry Bertsikas at MIT came up with various textbooks in extending this and using approximations, for example, neural networks, and he called it neurodynamic programming before being coined as deep reinforcement learning today. So naturally, you might ask, am I suggesting that we're going to have RL for batteries? Well, not so fast. This is the wrong tool, perhaps for the wrong problem. And my students have gotten very excited about applying RL for batteries, but the deeper we get into this, the more I realize that, when you have a hammer, you start to think everything is a nail when it's actually a screw. So my goal here is actually to highlight where how this method and problem are disjoint and what we've done to really align it. So in particular, reinforcement learning does not natively handle constraints, and fast charging is a game of constraints. That is, we want to pump as much current into the battery as possible while maintaining these electrochemical states in safe operating region. Also, RL typically requires many training episodes. And you can play the game of Go thousands, millions of times, make a lot of wrong moves, no big deal. However, charging many battery cells using random currents is not only untenable, but potentially very unsafe. Moreover, reinforcement learning assumes state measurements, and we generally cannot measure the electrochemical states in the cells. So, had a video here. Let me actually just skip that. If there's a question, I can show it later. So the research objectives are to natively handle these constraints under uncertainty, because generally these models are uncertain, and to learn safely. That is, as we're training the battery to charge faster and faster, we want to do it in a conservative way where it's not being too aggressive to enter, for example, a thermal runaway event during training, and also overcome the state feedback requirement. The first two we're going to accomplish today. The third is some ongoing work. So my goal is really to explain the essence of this problem and the solution that we've come about. And just to explain a little bit more on reinforcement learning, what it is this feedback control architecture where you have this environment, which in this case is the battery. Let's see if I can write this. The environment in this case is the battery, and then the state is the internal electrochemical states that we measure or infer, and then this agent is the controller. Now, importantly, the feedback that we get is not only the state, but a reward that indicates how well are we doing in terms of fast charging this battery. And then given that data, we will then take some sort of action. Okay. All right, so what I want to do next is just give a primer on optimization, just to give you a sense of the essence of the problem and the solution that we've come about. Now, ultimately, this is an optimization approach. As one of the poster presenters said, all this machine learning and RL approaches tend to be optimization problems. And a classic formulation is to maximize f of x, where x is our design variable, subject to some safe constraint, for example, g of x less than or equal to 0. Now, in reinforcement learning, by far, the most popular way to address this is to do what they call reward engineering. So it looks something like this. I'm going to take my objective function, and then what I'm going to do is add a penalty to it, where when g becomes positive, that's when I violate it. That's when I'm going to activate that function, and then it's going to reduce my reward. So I'm going to punish it. The problem with this is that we conflate our objective to charge quickly with our other objective, which is to keep the states in a safe operating region. And because of this, tuning alpha that does this trade-off is highly non-trivial. It requires significant calibration, lots of episodes, lots of training. It's referred to as a hyperparameter. And moreover, this function g, which encodes our constraints, is uncertain. So we do our best to mathematically model what are the constraints in these batteries, but there's still some level of uncertainty. Moreover, if we use simplified models, there's always some approximation error. So conflating the constraints along with the reward here is in fact what we need to avoid. So classical RL methods will not work for battery fast charging if you conflate the constraints with the reward here. Okay, so now I'm going to have a slide on a bit of math just to give you a sense of what's going on here. So something perhaps a bit different. And again, I just want to give you a sense of the essence of our innovation here when it comes to safely charging batteries quickly. So let's imagine here we've got this constraint, g less than or equal to 0, but there's some modeling error. And I'm going to represent this as a random variable. Call it big R. And red means random in my slides here. Now, if I have this random variable and I want to satisfy this inequality, I can do so if, for example, I know the cumulative distribution function on random variable R given by capital F, which is the probability that random variable R is less than some given value little r. Okay. So we can formulate what's called a chance constraint. So the idea here is I'm going to say, well, I don't know what g plus r will be, that sum will be random, but I want that their sum is less than or equal to 0 with some probability, 1 minus eta, or imagine eta being some safety factor. So for example, it could be 0.01, for example. Whoops, that's the decimal point. And if I do that, I can just move minus gx to the other side, and I have the definition of a cumulative distribution function. My random variable is now replaced with this CDF, and if I know this CDF, then I can just rewrite my constraint in this way. So this is beautiful, nice and clean. Even with some uncertainty, if I know the statistics in terms of the CDF, then I can robustify, if you will, this optimization problem in reinforcement learning. But the problem is that we don't know generally the statistics on our modeling error, because to do so, we'd have to know what truth is. So this leads to what's known as a distributionally robust approach. So just notationally, let me define the true distribution for R as P star. This is the probability distribution, the true one, but unknown for R. And I'm going to denote by P hat an estimated distribution from empirical data. So from my experiments or simulations, I will collect data. I can see how close I am to violating constraints. And then I can build an empirical probability distribution here that's P hat. Now, Borel's law of large numbers says if I get more and more data, P hat should converge to P star. But in the meantime, I'm going to have some error. So now what I want to do is consider a family of these distributions centered around P hat. Imagine it as a ball that's centered around my empirical distribution, where any given distribution in this ball is a distance no more than epsilon away. So essentially what I have is this picture where I've got this ball in the middle, I've got P hat, right? And then this ball is of radius epsilon. And I'm interested in probability distributions that are the family of probability distributions in this ball. Okay, so now what I can do is apply this constraint, but for the worst case distribution in this ball. That is, I can look at all the distributions in that uncertainty set in that ball, figure out which one is the worst in terms of potentially violating this constraint, and use that one. So this then leads to the following. So why does this matter? What does this mean for batteries and fast charging? Well, if I have this particular constraint, it turns out that there's a lot of really active work in the past 5 years in robust optimization, where you can in fact reformulate your constraint into a super clean one that looks as follows. G of x plus q, where think of q as some sort of buffer, okay? Sorry, q is some sort of buffer. And it turns out that the safety buffer will actually go to 0 as this uncertainty set epsilon goes to 0, which can occur as the number of data samples you have goes to infinity. So for example, you might be asking the question, what is the size of this ball, right? Which is centered around my empirical data. So I take some empirical data. This is the distribution for the error in the model for my constraints. I have some uncertainty set epsilon, but this uncertainty set epsilon is a function of my data. And as the amount of data goes towards infinity, then I can become more and more confident because P star should, or I should say P hat, gets closer and closer to P star as I gather more data there. Okay. So now I'd like to introduce an extension we've made to Q learning called distributionally robust Q learning, or we like to call it Dr. Q. So it's an extension of Watkins Q learning constructed on constrained Markov decision processes, because the fast charging game is a game of satisfying constraints. And interestingly, the Q functions associated with constraints are learned online, but safety is robustly guaranteed with this distributionally robust idea. So I just want to give you an essence of the idea so you can appreciate some of the math behind what makes this works with the results that I'll show you soon. So I liken this to the analogy of when you're a kid running around the pool. I did this a lot when I was a kid and probably was a little unsafe in doing so. But perhaps when you're young and you're a little less uncoordinated and you've got more uncertainty about how you move, you might sort of leave this buffer between the edge of the pool and where you're running. But as you get older, you get more coordinated. The mathematical model in your mind for how your body moves and in your interaction with the corner of the pool gets better and better. So over time, you might get tighter and tighter so you could race around the pool with your sibling faster and faster, but not fall in the pool. Do it very carefully. So now let's apply this to batteries. So what I'm going to do first actually is apply this to the equivalent circuit model. And I'm going to do this for a couple reasons. The equivalent circuit model is a simple model used in 95% or more of BMS type applications. But the other reason that we are applying it to the equivalent circuit model is because we can actually calculate the provable optimal solution with a simple model like this, whereas with a more complex atomistic or Newman style model, we wouldn't be able to do that. So we can actually benchmark Dr. Q against the optimal solution with an equivalent circuit model. So it's this type where we have two RC pairs and internal resistance in series. And the goal here is to go from some initial state of charge, like some low state of charge, to some target state of charge. And what this reference is saying is I want the state of charge to track as closely as possible to my target. Think of something like 0.8, for example, SOC, as best as I can over this finite time horizon. So T going from 0 to capital T, while satisfying these constraints. And I also have voltage limits here, which will play an important role. So what I get is, what we get is the following. So our approach is this Dr. Q, Dr. Q that's shown in green. The optimal solution is shown in blue, which is the mathematically provable optimal solution. And then DQN is deep Q network. So this is an extension of Watkins Q learning, but using these deep neural networks. Now, it turns out that with no knowledge of the model a priori, starting with nothing, we can train the controller to get reasonably close to the optimal solution shown in blue. And what you can in fact see is that with a bit of measurement noise, it's a bit conservative in terms of not violating this voltage constraint. So you can see it carefully approaches it. In contrast with DQN, it just randomly tries different actions. And in the process, what you're going to get is this unsafe trajectory where it violates the voltage constraint. So this is what I mean by RL off the shelf isn't going to work for batteries. It can be unsafe and it doesn't really make sense. So this approach with distributionally robust Q learning seems to work a lot better. Okay, and that's better appreciated on this next slide. In fact, if you run DQN 10 times and you run Dr. Q 10 times, you can see the volatility and the performance on the right here. And DQN is going to give you large volatility in the performance. This is how well you're tracking SOC. Whereas, in contrast, this Dr. Q is much more reliable in terms of trial to trial, giving you reliable results that are approaching the optimal solution, the optimal reward shown in blue. And that's also illustrated on the right, which is perhaps what I think might be the most interesting plot in this first section, where what we're showing is the cumulative number of constraint violations here in the maximum constraint violation in voltage. And with Dr. Q, you can see in the beginning, there's a couple, but then after that, it's safely away from these constraints and then is approaching it closer and closer progressively as we approach that boundary, yielding safe learning during trials, as opposed to DQN, which is going to make some very unsafe actions, then some safe ones, and eventually try to converge around the optimal solution. Okay, and actually, I have a video of this, which I think I'll be able to show. Hopefully you can see. And what you're going to see here is actually the trials going by. So in fact, this only takes about 15 to 25 trials. And you can see the first one is at a low C rate, and it progressively increases and increases and gradually approaches these constraint boundaries. You can see why I say it's like being conservative, running around the pool and then going faster and faster. So this is quite exciting to us because it means that we can safely use these learning-based control methods for applications like batteries. And we've extended this to the single particle model with electrolyte. Here's some simulations on the left where you've got more complex dynamics, more complex constraints. I don't want to emphasize too much on that. But in the end, what you find is that the solutions all basically look the same. Pump in as much current as you can while ensuring safe constraints. So along with that, we've actually also done a little bit of mathematical theoretical work, and Se-Hong Park has actually used Pontryagin's maximum principle to prove the following, which is very nice because once this is understood, then you don't have to bother with doing some more complex algorithms. It turns out that if you idealize a battery as a single particle model-like model, okay? And your goal is to maximize the state of charge over some finite period. That is the fast charging problem. And you've got some upper and lower bounds on your constraints here. Then the optimal solution will always be bang or bang ride. So bang means just maximize the current until the end of the time horizon, or if a constraint is going to become active, that is you're on some safe boundary, then you're going to maximize the current and then ride on the constraint boundary. And by the way, the constraints here can change over the period of time. So for example, in this SPMET model, and actually Candler Smith highlighted this in his talk, you can see that it immediately depletes electrolyte on the backside of the anode here, and then you're riding that constraint. Meanwhile, while everything's relaxing, at some point you're going to hit a temperature boundary, and then you're going to ride that constraint. So you've got this bang ride, and then the constraints, the order of the constraints could actually change over time. So given this insight that the optimal solutions, at least for these simplified models, these single particle-like models, look like maximize current, but ride these constraints, namely the dominant ones, which could change, that then leads you to think, well, perhaps we could just have some sort of algorithm which maximizes current, but then ensures the constraints are satisfied. So this leads us to what are known in the controls business as reference governors. So once again, just to remind you, we're trying to move from this paradigm on the left to the paradigm on the right, where if we understand the internal electrochemical states, we can apply boundaries on those to maximize performance and better ensure safety. So let me highlight two pairs of very interesting constraints. So the first is constraints on the surface concentrations of the particles in these lithium-ion batteries. So here we've got upper and lower limits, which are described by these blue boundaries that are oriented in a vertical way here, okay? Also, we have these nonlinear constraints which represent lithium plating. So for example, in the anode, lithium plating, which it turns out forms a curve like the one shown here in the slide. So just to emphasize, this top constraint can represent lithium plating. Now, what this all means is that the feasible set, that is the region we want to stay within, is this green one, and we don't want to enter this red one. So this is the safety envelope that we're concerned with when it comes to fast charging. So the game is to stay within that safety envelope and not venture outside. Now, Luis Cuoto, who I believe is at Oxford right now, and is also a postdoc at ULB, has been working on reference governors for batteries. So the idea of a reference governor is to enforce these constraints. So what it does is you give it some desired state of charge, like 0.8 or 0.9, and what it does is simulate a model forward and determine if it violates any of these constraints. It'll then determine the largest current possible to achieve this reference state of charge, while ensuring that the constraints are not violated. So it works something like this. Let me just give a cartoon. And this is a cartoon by Emanuele Garrone, who's one of the co-advisors of Luis Daniel Couto at ULB. Super funny guy, and he makes the best analogies, so I'm going to borrow this one from him, especially because I'm trying to maximize the number of media references in this presentation. So imagine that you have this nuclear power plant with some measured state, and you have some existing controller around it, like a BMS in a battery or proportional integral derivative control for this nuclear power plant, and you apply some reference commands, some reference set point. And then here comes the user and says, here's my desired set point that I want to move the system to. And we plug these things together, but unfortunately constraints could be violated, and then we're in trouble because something unsafe happens, and that's no good. So the idea here is to put some sort of block in between the desired reference and the applied reference, this reference governor, given by this pretty graphic that suggests it's AI. It's not AI, it's just mathematical models of batteries. That's it, what this community works on. And we're going to use that mathematical model to check if we're violating constraints. So the idea is that we're given a desired reference. We want to generate a modification to that reference, which guarantees safety, but tracking that desired reference as closely as possible. For us, that's going to be keeping the battery state of charge at some high value that we're trying to charge to. So what Luis did prior to being, when he was at ULB and also when he came to UC Berkeley as a visiting PhD student, was assemble this extended Kalman filter, which brought man to the moon in the back, along with a mathematical model of the battery and this reference governor. And we did these closed loop experiments inside our lab. So here's a description of our lab here, where the Kalman filters that estimate the states, the controller, the reference governor, are all embedded in this microcontroller. We have the battery tester, which is charging and discharging the cells inside an environmental chamber, measuring current voltage and temperature. We're using that to estimate internal states. It's then optimizing the charge cycle based off this reference governor approach. Now, let me also highlight that these experiments were done with 18650 NCA cells, very similar to what's in previous generation of Tesla vehicles. So these are very much energy cells, cells that are really designed for maximum energy capacity as opposed to power per se. So here are some pictures where you can see the cells inside the thermal chamber. You can see here how we are measuring temperature at the surface, and then we have 4-point measurements to measure voltage, and the load is provided by that PacCorp SVT 2050 test system. Okay, so now what I want to do is show you these results, and here's the punchline. The punchline is going to be that it turns out with this reference governor, we can charge faster without degrading as fast as a typical constant current, constant voltage measurement using these electrochemical or reduced form DFN type models. And before I actually show you the results, I want to be super honest with you. I always wondered if some of these models were nonsense, and if in practice they really can do something in terms of control when it comes to improving the performance. I was always kind of skeptical about this despite investing my whole career into it. Once Luis did this, I'm now convinced that these reduced form DFN type models, they're definitely getting the right aggregate behavior. And if we use them in a control loop, they are definitely improving things. So I'm very optimistic from these results. So let me share them with you now. So what I'm showing you is a comparison of the reference governor against CCCV. So 1C and 2C, these represent constant current, constant voltage. So let me write this down. We have 1C and 2C CCCV cycles. Okay, those are the triangle and the squares respectively. And then we have the reference governor, which is given by these circles. So what you can see is the capacity fade, which goes quite rapidly because these are energy cells, for these different cycles. And what you can see here is that the reference governor use an appropriate color. The reference governor is decaying at a rate that's similar to 1C CCCV. These squares here are 2C CCCV. So whatever is happening, it seems that the cells are aging roughly as quickly as 1C CCCV. Now, what about speed? So this shows the fast charge times as a function of cycle number. And interestingly, you can see in the beginning, 2C, which are the squares, are going relatively fast. But over time, because we have the capacity fade and internal resistance building up, it's slowing down. And the reason for this is because the CV portion of the charge cycle is getting longer and longer and longer because we're hitting the voltage limit much sooner. Meanwhile, you have the reference governor that's trucking along at much faster speeds here. You can see there's a bit of noise here, and that happens to do with the fact that we're actually resetting the parameters of the model every time there's this vertical dashed line. So the data is a bit messy because it turns out that we relearn the model every few dozen cycles. So it seems that we're charging faster, and the capacity is fading at something that's commensurate to 1C CCCV. And in fact, you can take the ratio of these two things, and that's what's on this plot, which basically shows the average current, the capacity per charge time, basically how much current that you're pushing through the battery. And you can see that the reference governor is in fact doing better than these CCCV methods. Now, mind you, this is in contrast to what Will Chu found in his results, where you can see from his recent paper, you get these constant current-like cycles. Now, he's using an LFP cell, we're using NCAs, so that needs to be kept in mind. But let me give you a little bit more insight into these constraints. So here now, I'm showing those constraints that I showed earlier on the left-hand slide. And then in red, in this reddish yellow color, this is what, this reddish yellow color is the trajectory that the reference governor is taking. So what you can see is it injects a bunch of current at first, it then hits this constraint or slightly overshoots it, and then rides this constraint, which tries to keep the cell away from this lithium plating constraint. It turns out that a CCCV strategy, what it'll do is it'll apply some constant current, and then it'll hold that constant current. But if it holds it too long, eventually the cell is going to enter into this region where lithium plating can occur, okay? And this is why 2C CCCV is in fact aging quicker. Now, interestingly, if you look at the constraints as defined on voltage and current, CCCV, essentially what it's doing is it's setting this constraint boundary, right? We've got this upper and lower limit for voltage. The voltage lower limit here is slanted because it depends on the current that you're applying here. Now, this constraint is really a proxy to try to not violate the lithium plating constraint and other things. So what you can see is, in fact, this reference governor approach, what it's essentially doing is it's allowing the cell to venture outside of this constraint, which is the one that we actually are using as a surrogate because it's the only thing we can measure. And what it's doing is using knowledge of the internal states, it's actually ensuring safety in this domain. And that really is the key to what's happening. And here's another picture just to show the purple box shows the constraints with CCCV. And you can see here that with CCCV, at some point you can actually venture into this unsafe portion. And by unsafe, I actually mean you enter into a region where lithium plating will occur quite quickly. Okay, just a few more slides. Now you might be curious, what do these profiles look like? So this slide is quite busy, so let me just highlight a few areas of it. So I want to focus your attention at this top plot first, which is showing a zoom of the current. What you can see is that the reference governor, what it's actually doing is injecting a large amount of current very quickly over a short blip, which is bringing us to that boundary where we're hitting that overpotential, or actually there's a safety region before that. And then the portion along here, it's riding along that constraint. And the current trajectory looks like this. So we actually get a shot, like a bang of current, and then it's riding that constraint. Now, interestingly, when you do that, the temperature is not building up. And in fact, you can see that the temperature overall is not building up much in many of these methods. And it suggests to me actually that SEI growth may not be dominant here. It's really lithium plating that we're worried about. That's in contrast to, say, that recent paper by Will Chu, where we have LFP. And but as Candler-Smith pointed out, the game we also want to play is, it's also good to elevate temperature slightly, because then the transport effects of the electrolyte are faster, and that constraint may not be the dominant one. It'll in fact loosen, and then that'll allow you to pump in more current. So there's this careful game that it seems that the algorithm is playing between ensuring constraint satisfaction, but exploiting the dynamics to charge more rapidly. Now, I don't expect these results will be exactly the same in other chemistries. The point is really the framework here. So now I'm going to summarize so we can have some questions. What I started out with was describing to what extent can we use reinforcement learning. And the key takeaway I want you to have is not so fast. Don't just apply these things off the shelf. We're not playing games. Literally, we're not playing board games where we can just do a million trials of unsafe things. And that's why industrial RL needs to be thought about in a very careful way. And batteries is one example of that. What you can see is that we came up with a methodology, an extension in reinforcement learning called distributionally robust Q learning, to progressively get a little bit more aggressive in terms of charging the batteries. And then once we understood what the shape is, or the nature of the optimal solution is, it turns out that reference governors are really a nice approach, even with these surrogate models, which only approximate what's happening, but they seem to get the right trends, as we've seen from this data. So with that, I want to thank my group. We have a large, diverse group contributing to all this research. I just get to share it all with you, and they do the hard work. And this group is in fact doing everything from batteries up to electric vehicles, automated vehicles, and we also do a lot of work in grid scale applications, fleets of EVs, EV charging stations, distributed energy resources. So thank you very much for your attention. Please feel free to visit us, download publications at the website here, send me an email, send me a Slack. Thanks a lot for your attention.
Great, thanks very much, Scott. That is another really, really amazingly awesome presentation. We were all gripped here, enjoyed that very much. Now, I don't know if you've got access to Slack or not. If you have, there's a few questions popping up there. If not, I can just read them to you or share my screen. What would you prefer?
I do. I have it here on my second monitor.
Okay.
So,
by the way, I love your the way you're writing on your slides. You'll have to tell us how you did that, because I think we're all going to be having to do that over the coming weeks.
We're all getting very good at Zoom here, aren't we?
Yeah.
All right. Do you want to facilitate, or should I just grab them as I see them?
You go for it. If you can make it work, then go for it.
Okay. So Jorn Reiners, let's see. Have you compared this approach with a conventional offline optimization, which produces a charging protocol purely based on the model? Yes, we have. We've actually compared both. We've compared both. That is, we've compared this Dr. Q and the reference governor using offline models, and we've done a number of publications on these offline methods, using, for example, pseudospectral optimal control. And the solution tends to be the same. So it's funny that we're trying all these different methods, and we tend to get the same ultimate effect: maximize current and then ride the constraints. So there's a lot of methods out there. I think we need to think very sensibly about which makes sense, given the context of what we can test safely and how much uncertainty do we have in the model.
Yeah, I would agree with that. And perhaps I can jump in and say, uh, it is difficult to know with, I mean, I like your hammer picture at the beginning, and I think it's a tricky one, isn't it? Because I think as a kind of community, I'm kind of speaking honestly, the control community is very motivated to come up with new theory, if you like, or new kind of, yeah, sort of quite theoretical stuff. But actually, in the end, when you apply it to something, you often, as you just said, you often get the same results with many different tools. So you've got to ask, you know, is another tool really going to change the result or not? I'm just saying what you've said again.
Yeah, precisely.
um, so you can skip my question if you want, because I've just kind of talked a bit too much. Come back to it if there's time.
Sure, sure.
Can you
Tina
see the
has
other
a good
question? Yeah.
question, which is about applying uncertainty in the reference governor case. And the answer is yes. If you go to this picture, what you can see actually is that this boundary, we've actually put kind of this buffer region in between. Maybe I should use a different color, like a yellow. So we've actually pulled back a little bit on that just because of a bit of model uncertainty. This hasn't been done in a particularly rigorous way, but that is one way that we've accounted for uncertainty, particularly in the constraints.
Right.
Great. Let me actually go to Igor's question. So can one improve DQN if one sets, for example, a big weight to GX in the reward function or smooth along the line? Or is Dr. Q always better for constraints problems, irrespective of multi-parameters? Yeah, quite honestly, we've played a lot with this reward engineering. And in fact, we have one publication on it. And I've actually pitted two students against each other to see who could get the best results. And the question is really about, can you just set a big weight on alpha? So the problem with doing that, of course, is if you set a big weight on alpha here, then your algorithm basically does nothing. It'll say, just don't do anything. I don't care anything about charging the battery. I just don't want to get close to these constraints. So when you conflate the objective to charge fast, but stay away from these constraints, balancing this is difficult, and that's where you require a lot of calibration. It's been quite pleasant for us to see with Dr. Q. It just progressively gets more aggressive as it gets closer to the constraints, as you acquire more data and become more certain about your error.
I mean, sorry to kind of jump in at that, but I do wonder. Well, two things. One, what's wrong with traditional optimization algorithms, Gregory Boyd style? Sorry, Stephen Boyd, wrong person. And what do you think of Bayesian optimization in light of this?
Yeah,
just been mentioned a bit.
Once you try to add more physics into your models, you're going to increase the number of states. And actually, the bigger issue is not the number of states, but the nonlinearities. If your problem, you mentioned Stephen Boyd, who's really popularized and advanced the science around convex optimization.
Yeah.
If your model stays linear in the states, even when it's large, then you can use traditional optimization and has polynomial time complexity. But when we're adding Butler-Volmer kinetics, we've got diffusivities that are functions of concentrations and temperature. You want to vary porosity across the cell, as Candler Smith described in the design, very cool idea. Then these non-linearities will break convexity, and then you have this medium to large scale optimization problem, which is not tenable to solve, in fact, even when it's non-convex.
Right. Okay.
So that's the key issue.
There's a few more questions there. Maybe you just want to pick one.
Sure. So
one or two.
Yeah, let me scan through them.
There's one in the chat on Zoom as well.
All right, let me check. So let me quickly answer two, one from Brady and one from Dhamika. Yeah, Brady, with the computational headroom, this is really a game of how skilled are you in terms of coding up your model. So, and if you can make things linear or be very clever about linearizing in the right places, you can conquer that. So that in fact is less of a concern when you actually get into it than people make it out to be, we've found. So we've done this all online. And then Dhamika, to reparameterize the models with a reference governor online, that was actually a huge challenge. So let me highlight that, because that was quite difficult, and Louise can speak more to it. But if you go back to these slides, and you can see the reference governor is kind of noisy in terms of how quickly it charges. That's been quite difficult to take a batch of data and then re-identify the model. And so we're trying to improve that right now, get better methods for it, using things like Bayesian optimization that you mentioned, Dave, and a previous poster presenter was talking about. So I think that's really sensible for that type of application. And I also agree with Candler that this issue of model identification, parameter identification, still remains a nasty unsolved problem. So I certainly encourage the students that are in the audience, if you're working on that, keep going, bring your diverse, excellent ideas. And if you're looking to get more into this, then that's a great problem space.
Cool. Okay. Do you want to do one more? And then we'll call it a day, I think.
Sure. So
you might want to dive in separately and answer some of these just on Slack.
Yeah, so Peter asks, why do you think control approaches work even when we do have parameters with wide uncertainties?
Yeah.
It's a great question. It sort of, it gives me identity crisis, because as a control engineer, you know, it's based off these first principle models, and when the models are wrong, you know, that doesn't work well, which makes me particularly excited about these robust approaches, right? So if you've got some statistical knowledge of the uncertainties, or you can acquire data on it and build that statistical knowledge, then you can hedge and be a little bit more conservative and to achieve your control goal. So honestly, I think this is a really exciting area in a robust optimization that's been popularized in the past years. Really awesome ideas that are super applicable for the control of batteries and other applications that can help us manage this issue of getting good performance results like you saw today in the face of uncertainty.
Okay, great. Scott, thanks again very much indeed.